So the heat equation in Rn in general, so for R2 in the plane or R3 in 3 space or whatever you want to do, the derivation of it actually works just more or less identical to in one dimension. We just swap out the fundamental theorem of calculus with divergence theorem and a couple of other sort of higher dimensional basic calculus tools, but it's more or less pretty straightforward. So suppose we have the heat density in, well, let's just say R3 for right now. So this will be given by u of x1, x2, x3, t, but that's sort of a pain to write. So it's easier if we just take that spatial variable to be a vector. So, whoops, yeah, so x will be the vector x1, x2, x3, so that'll be our point in R3, and then we can just use the notation u of xt to describe the unknown function. And so what we're going to do is we're going to be looking at some picture kind of like this. So the idea here is that the blue region is omega. That's the area that we're interested in, and we'll just focus on some small ball B that's contained in omega. And then the thermal energy that you get that in some region is going to be the integral of the density over that region. And so let's see, so if U is heat density, then C times rho times U is going to give us the thermal energy, and we're going to integrate this over B. And so the notation that I'm using here is that dV, or d volume, this is dx, dy, dz in some order, or actually I guess dx1, dx2, dx3, whatever. Or maybe you want to think of it in polar coordinates. Doesn't matter to me, it's just whichever volume element you want to choose. Whether it's in Cartesian or in spherical. The dV there is just saying it's a volume integral, set the darn thing up however you like. So let's see, now that's how much thermal energy is in there. If we need to account for sources and sinks, then the rate at which energy the rate at which it's generated inside the ball is going to be the integral over the ball of F, wherever F is your external forcing function. So some function F. And then we'll also be looking at the heat flux through some small portion of the boundary. So if we have some region, say it looks something like this. So here's our little tiny portion of the boundary of that ball there. Then if the flux is coming out, say, straight horizontal like this, we look at the normal vector to the surface at this point. So this is the normal vector right here. I'll denote that with a little n. And then the amount of flux coming out through here is going to be found by projecting onto the normal vector. So that's supposed to be a projection. It kind of looks hairy, but oh well. And so if that's our flux, then the projection of the flux onto a unit outward normal vector is phi dotted with dn. And then you multiply that amount of flux over the entire little unit of area. So we have that much coming out. And then that's what we need to integrate over the entire surface. So integrate over the boundary of the ball with respect to area. And this is going to be heat flux coming out through this little patch of area. And so just to emphasize, n is the unit outward-oriented normal vector, meaning orthogonal to the tangent plane of the surface. Okay, so to get the conservation law, we look at the total amount of change of heat energy with respect to time, and say, well, that's going to be equal to the amount that comes out, so the heat energy is going to decrease by whatever comes out through the surface as flux, and it will increase by whatever is generated internally according to the sources and sinks F. Now, if we use the divergence theorem, which is the three-dimensional analog of the fundamental theorem of calculus, then that tells us that the flux through the boundary is going to be given by the integral of the divergence. So I write divergence as the del dot the vector. So this is the same thing as divergence of phi, which is what the book writes. And so if we make that substitution, then we can group everything under an integral over b. So bringing everything together, we have the integral over b of, and we have the time derivative of c rho u, and then we pull over the divergence of phi and subtract the sources and sinks, and that's supposed to be equal to 0. And then, since this is true for any small ball contained in the region we're looking at, the same reasoning allows us to get rid of that integral sign, and we know then that c rho u t is going to be equal to minus the gradient of phi plus f. All right, and so that is our conservation law for the heat equation in Rn. And all that remains now is to change phi into something having to do with u. And so for that we use Fourier's heat law. Fourier's heat law says that heat flows down the gradient, or phi equals minus k gradient u. So in words, heat flows down the gradient. Okay, and so here again, K is thermal conductivity. So it's a measure of how well heat can move around inside the object. So then the conservation law becomes C rho U T equals the divergence of, and then we have minus K grad U, and I forgot a minus sign out front, plus F, or 0 UT is gradient, or sorry, Laplacian of u plus f in the case when k doesn't depend on x. So if it's a uniform constant. All right. And so, yeah, the other thing that I wrote here is that the divergence of the gradient of u is equal to the sum of the second partials applied to u, and that is the Laplace operator applied to u. And that little calculation, so this one right here, that's a very easy one or a very straightforward one to check. So I will leave that up to you. And so in general then, the heat equation in higher dimensions is going to look like ut minus k Laplacian u equals 1 over c rho f, where little k here is equal to capital K over c rho, and this is diffusivity. And so that is our heat equation. And I wrote things out here as if they were for R3 back in the beginning, but if you notice, everything works for R2 or Rn in general, just the way it's done.